good evening to all the colleagues and friends connected to this webinar about the evolution of semiconductors from its beginnings to today's trends. I greatly appreciate the collaboration of our embassy in Singapore with Ambassador Victor Hugo Rojas and with Mr. David Lee, as well as the Department of Economic Diplomacy of the Direction of International Cooperation. Today, as the Director of the Diplomatic Academy, I am pleased to introduce to our special guest, Mr. Francois Guibert, who is a semiconductor expert with over 40 years of experience in Asia, the US, and in Europe. He resides in Singapore, where he has worked at companies such as Texas Instruments and SDM Microelectronics. He now offers lectures and consulting on semiconductors. Mr. Guibert's lecture will be on the importance of the semiconductor industry, highlighting how its development is crucial for current and future markets. I'm very pleased to have you here. Thank you so much. And I'm giving the floor to Ambassador Victor Hugo.
Thank you very much. ¿Usted lo tienes apagado?
Tienes que cerrar el tuyo.
¿Cerrar el mío? ¿Cómo? Ah. No, eso lo tienen que hacer. Can you turn off the microphone for Mr. Guibert? So the ambassador.
No.
Oh, there we go. Okay.
Close the Guibert because if not, it's a feedback because we are in the same room. And reduce the volume in the computer.
Okay.
Okay. With the permiso of the Fabriz, I want to speak in Spanish. Hola a todos, ¿cómo están?
Es un verdadero privilegio tener a nuestro amigo aquí. Yo voy a dar este pedacito en español y después nos vamos a seguir conectando en inglés. Yo quería nada más destacar la importancia de lo que es la industria de los semiconductores en Costa Rica, trazando un paralelo con lo que representó el café en nuestra historia. En el siglo XIX, el café no solo transformó nuestra economía, sino que también nos conectó con el mundo. El grano de oro trajo desarrollo, educación y mejores condiciones de vida para nuestra gente. Gracias a ese auge fuimos capaces de emprender grandes obras como la misma construcción de nuestro icónico Teatro Nacional, símbolo de progreso que nos brindó la exportación del café. En 1986, Costa Rica exportaba principalmente productos tradicionales, de los cuales el banano, el café, el azúcar y la carne representaban aproximadamente el 77% de las exportaciones totales. En el 2023, las exportaciones de productos tradicionales representan solo el 9% de nuestras exportaciones totales. Las exportaciones no tradicionales ahora están lideradas por bienes manufacturados de alto valor agregado que representan la mayor parte de lo que Costa Rica manda al resto del mundo. Los semiconductores ahora juegan un papel similar al que alguna vez tuvo el café. Son el grano de oro del siglo XXI. Al igual que el café, esta industria está impulsando nuestro crecimiento económico y ha puesto a Costa Rica en el mapa global de la tecnología. Las empresas líderes confían en nuestro talento y producimos componentes esenciales que se usan en teléfonos inteligentes, autos eléctricos. No solamente nos dan empleos de calidad, sino que también fortalecen nuestro posicionamiento en la innovación y la tecnología avanzada. Los jóvenes de hoy, ¿verdad? Yo ya no soy tan joven, verán que en los próximos años, los 20 próximos años, verán unos cambios significativamente acelerados e importantes, y eso va a impulsar mucho la industria de Costa Rica. Así como el café definió nuestra identidad en el pasado, los semiconductores van a marcar el rumbo del país en el futuro. Así que esa es la importancia de conocer a fondo en qué consiste la industria de los semiconductores, y por lo cual pues realmente agradecemos muchísimo que Fabriz take the time to be with us tonight, because now we are in Singapore at 10 p.m. switch to speaking English. And now the floor is yours, my friend.
Thank you. Thank you very much. So good morning. It's a great honor and pleasure for me to have the opportunity to make my conference to the Costa Rica authorities. And I will start immediately by telling you that indeed the semiconductor is intelligent steel of the 21st century. Just very quickly, I have been introduced by the ambassador, but just to mention that indeed I am now a consultant, but I have had a long career from almost 38 years in the semiconductor industry. But not only I work in this strategic industry, but I have also done a lot in Singapore for the business community. And you can see on my resume that I have been the president of the European Chamber. I have been 5 years at the Economic Development Board of Singapore. I've been also the founding chairman of the EU-ASEAN Business Council, headquartered in Singapore, and the chairman of the advisory board of the Singapore Semiconductor Industry Association, which, by the way, was having a few days ago his annual summit in Singapore with 1,300 people. Now, the content will be the following: the definition of semiconductor, because it's a word now which is very well known and almost fashionable, but very few people knows exactly why it is a semiconductor. Then we look at how do we design a complex integrated circuit, a chip. Then the manufacturing process, which is rather complex and with high intensity of the capital requirement to do so. Then we will have the chance to look at the history, because this industry is not well known by even the educated grand public. And it is interesting to see what was the history of the growth of this industry in the last 75 years, and what are the countries which has been successful and the ingredient of success. Then we look at how do we move in this industry from supplying industrial need to answering society call. And this is very significant for the volume of the semiconductor industry. Then I will give you the picture of the top 20 players landscape and their manufacturing challenges, as well as at the end showing you the strategic importance, if not the vital role, in the worldwide economy of the semiconductor that I'm sure you have seen in the last 3 years, when everybody was complaining that there was not enough chip, that was delaying the growth of a lot of other industry in the world. Now, let's move to the next one. Yes. So why semiconductor? On Earth, there is basically two kinds of elements, the insulator and the conductor. The insulator, the rubber, plastic, mica, quartz, glass, and so on, are the ones that doesn't provide the ability to conduct current. The conductor are, in fact, the opposite. If you take copper, silver, gold, aluminum, if you put a little bit of voltage, immediately, let's say, it works, the current is moving around. Why? Because it's due to the atomic structure of the insulator and the conductor. If the electrons are far from the nucleus, therefore they can really escape and move to another atom and so on, and the molecule, and therefore the current is moving. On the insulator, that's the opposite. The electrons are so close to the nucleus that they cannot move almost, even if you put 200 volts on it. Now, semiconductors are in between. Naturally, they are an insulator, but if you put just a little bit of voltage, they become like a conductor. So this is something very peculiar. Arsenic, boron, polonium, silicon, germanium, and so on are the ones that are really insulate, let's say, semiconductor, because they are the melting point between insulator and conductor, and you can have, therefore, current or no current, which means 0 or 1, and this is the way that the digital world is moving. Now, what was invented in 1947 is a transistor, not the one to listen to the radio, the one, let's say, that are at the core of the silicon to be sure that you can provide the ability to create 0 and 1 and combine them all together. So the transistor has an emitter, a collector, and a base. On the base, you put a little bit of voltage, or you put no voltage, and therefore the electron can work between the emitter and the collector, and there is current. If there is no voltage, there is no current at all. So if we, by such capability of the transistor, we can set up basically mathematical function very easily with each transistor combined all together. So you can make AND or OR function, you can make very sophisticated addition or multiplication or very complex mathematical function by assembling the right transistor together to perform mathematical function between 0 and 1. That's the Boolean algebra, which is well known by mathematicians. Now, when you are, let's say, doing a function, you can, from your computer, you can call the macro cell, which have already been defined, and you can set up the design of the function that we want to realize in your silicon. From this tape that will incorporate the design of the circuit, specialized company will do a photomask. So photomask is like, you know, when you were doing photography before, you remember that there was a film and you were exposing to the light and you were having the paper below and you can duplicate the picture on the paper. Here, there is a set of masks and you can duplicate each level of the design phase on the silicon. Now, let's move, in fact, indeed to this manufacturing, because the most complex part is indeed to integrate the design that you can see on the right side with the set of masks on the silicon and duplicate many times on the same slice of silicon. And at the end, you will cut every of this piece of silicon and put it in a frame to be sure that you can protect this piece of design and use it in many electronic applications. Now, indeed, the manufacturing is from the design to put it on the silicon. The silicon wafer, which you have here, what I call sliced blank silicon wafer, is coming in fact from the sun. It's a very easy, natural element in the world, and it is treated thermically and chemically to have an ingot of silicon that later on you extend by almost a few meters and you slice it. And you end up by having the basic slice of silicon that is at the core for the manufacturing of integrated circuit and chips. So there is two major steps after taking the basic raw silicon and putting the design on it. There is what we call the front end, which is the most complex and capital-intensive one. That is really, let's say, putting the design of your circuit inside the silicon wafer. And then you have the back end where after having the die cutting, you will put it in a lead frame and make the bonding with the input and output and put it in a package to protect the die inside. Now, let's look at the front end first. And I will not go in detail technically, but you can see that there is a lot of steps, starting with the photo masking and lithography. It's exactly like the picture, the photography a long time ago, where let's say you have a lens and you have a very extreme deep UV light that is going to make the incrustation of the transistor and every transistor within the design inside the silicon. You can see in the pictures the detail. You have a deposition of silicium and then photoresist. Then you have the light exposure with the photomask. And at the end, you end up by the last one, which is photoresist removal. And you have created the transistor, the emitter, the collector, and the base. And you have to do that for the whole design, which can be sometimes very complex and very high level of number of transistors. All the rest I will go quickly because it's all the big machine that you need to make the deposition, the doping of the transistor to be sure that the electronic conduction is even enhanced, then the treatment by at very high temperature to fix it on the silicon, and then if you will have a film deposition, and you will repeat again all the steps that I was showing before to end up by the design of the chip inside and duplicate the chip on all the silicon. It looks very complex, but it is indeed. I will show you some pictures. This is a typical front-end manufacturing in semiconductor industry. And you can see how complex the machinery and the robotics is inside the manufacturing plant. Now, some of the machines are extremely costly. For the photolithography, which is the one that will allow the creation of the transistor inside the silicon, you have machineries that could be for the extreme UV and the very sophisticated technology that can cost. Each machine can be in the range of $200 to $250 million each machine. And you have to duplicate that, of course, 10 times or 20 times. So that's the reason why front end is a very expensive investment and very complex manufacturing process and science. Now, then we go to the back end. The back end is, in fact, you make the wafer dicing. That means that you cut every die on the wafer that has been duplicated during the manufacturing process. You take each die, you put it in a lead frame, you put the bonding for the connection of the chip within the output, you put some resin molding to protect it, and then you have the laser marking and final test of the chip. The one that you see on your left, on number 5, is the final product that are used in many applications in electronics. And here you can see in the back-end operation how complex also is the manufacturing process. Here you can see the detail of the die, the bonding of the connection and the input of the chip. And you know, there is maybe 100, 200 or 300 connection here, and the machine can do it in just half a second. So this is extremely complex manufacturing machine also to operate the back-end operation. Now, what do we do with the chip? Well, we combine it on a board with other chips. For example, this is a typical phone, and you can see inside all the chips that are going to be together for the processor, for the modem, for the communication, for the codification of your voice, for the memory, for the display, for your keypad, and so on. So you feel that you buy a phone, but in fact, on a pure hardware standpoint, you are buying semiconductor for 85% of it. Now, let me tell you that this didn't happen, you know, just in one day. On the next page, you can see how it was started. This is on the left side, 1947, the first transistor that was created by the Bell Laboratories by a team of people under the leadership of William Shockley. And this first transistor, you can see that there is a kind of link, and you have the emitter, the collector, and the base to set up the voltage on it. So this one was 4.6 centimeters square. And then there was the first integrated circuit, the combination of transistor in 1958, then the first microprocessor, then the first memories and processor CPU. And you know, in 2021, IBM Research started a 2 nanometer. 2 nanometer is a pitch. That means the distance that you can define between two transistors. 2 nanometer is like if you were taking one of your hair, the dimension of your hair diameter, and you divide it by almost 1 million. So this is, let's say, very small density. The highest technology possible today is 2 nanometer between each transistor. And you can see that, in fact, the size of each chip that you see on the picture is also 4.6 centimeters square for the chip itself, duplicated on the wafers. And each chip is having 50 billion transistors. So you can see that in 70 years, on the same area, 4.6 centimeters square, there was only one transistor, and today you have 50 billion transistors on the same area. This is absolutely exceptional. Now, the semiconductor industry is, why do we do this race of having the transistor becoming so small and so close together? Well, this is the first Motorola phone in 1983. You needed at the time 10 hours to charge it. You can speak only 30 minutes. The weight was 1.1 kilo. The price was $4,000 at the time, so that means $10,000 today. And you can do only phone call in US. And if you look at, I took an example of a Chinese one, Xiaomi, you can charge it in 3 hours. You can talk 35 hours. The weight is less than 200 grams, and it costs almost less than $100. And you can do phone call, camera, internet, audio, music, GPS, all what you are currently using on the cellular phone of today. Now, so this is the reason why you can have now your phone in the palm of your hand and not, let's say, a machine in the trunk of your car. So the volume of semiconductors started by the mainframe computer and switching system, but then move more and more on large volume every year, every 10 years. So you have then the starting point of the TV and the printers, and then the office equipment, then automotive, then smart card, and the cellular phone. And the volume for each application is not anymore 1 million, like for the mainframe computer, but is 1.5 billion. So volume of semiconductor is increasing by the emergence of a lot of new application, but also there is a second reason. The fact that inside the same application, the semiconductor content is becoming more and more intense, more and more in volume. So a TV of 1970 was having 5% of chips. All the rest was electronics only. Today in a TV, you have 70% of semiconductor. The same for your car. It was a few dollars under the hood of your car, and today it's almost 15% of semiconductor in some very high-end electrical vehicle. The same for your phones, the same for your PC, and whatever, even consumer devices. Now, but this didn't happen by chance. I wanted just to show you how, let's say, the computer has been moving in 70 years, 75 years. The ENIAC was the one in 1946, before the invention of the transistor. It was done by tubes. It was really, you needed a building of tube with 35,000 tubes to make just addition and multiplication on this huge building of tubes. Today, you can, in a microchip and on this quantum computer, you can do 1 billion of operation in 1 second. That's a big difference. So, but this was not coming also from scratch. If we look at the evolution of semiconductor, it started in USA, then Europe tried to catch up, was not successful on computer, but was later on telecom. Japan arrived in the 1970, 60, 70 with the consumer. And then you have a kind of pack of ASEAN region, Korea, Taiwan, Singapore, and China later on, that in the 1980s, year 1990s, appear on the landscape of semiconductor industry. And you still have a lot of other potential regions of the world, like India, like ASEAN, Latin America, Africa, that could become in the next 20, 40 years, not tomorrow morning, but also the place to develop semiconductor industry, which is so strategic today. So let me tell you, give you the picture very quickly on each of the countries which has been successful. You have US, of course, that started first, and it's a combination between equipment and components for the space and defense electronic. It was just after the war of 1945. So then there is the emergence of Silicon Valley in California in the 1970s, and this was very powerful in the sense that it was a combination of hardware and software engineering capability at the same place, with also the ability to do manufacturing of electronic system and semiconductor system. So US became leader in many areas, software, data center, semiconductor, and so on. And you have the name on the right side, on the very successful players on PC, datacom, and semiconductor leaders from US. If you look at Europe tried to compete on the mainframe computer business and switching system, but didn't succeed. However, in the 1970s, 80s, they came back with some good telecom industry with Nokia, Ericsson, Siemens, Alcatel, Thomson, and so on, and also on some automotive customers. And there was some program to support from the European Commission the development of semiconductor for this application. And Europe became quite leader on automotive, telecom, and smart car. And you have the name of the 3 leaders in this industry in Europe. The one of Japan was also quite interesting. They started in the 60s with the audio cassette. For those who are a little bit, let's say, an age above the young people, there is the cassette that was really starting to use semiconductor, then the TV, and then the video recorder. At the time, Japan became the winner of the standard of decoding and encoding for recording. Therefore, companies like NEC, Toshiba, Fujitsu, Hitachi, and Mitsubishi became very strong in semiconductor. In fact, when I was in US myself in the 1980s, middle of the 1980s, this company were already almost the top 5 of the semiconductor worldwide. However, Japan didn't succeed to maintain this leadership and was catch up by, in particular, the semiconductor from Asia. And their leadership in consumer, in robotics and semiconductor is still there, but in a lesser scale than it was before in the 1980s. And you have basically Toshiba and Renesas remaining, let's say, very visible in Japan. Now, if we look at the next one on Korea, Korea was started much later in the middle of the 1980s, and Korea benefited from the chaebol concept, where you have a big conglomerate having all the ingredients for the success. The banks, the consumer electronics, the distribution networks, the semiconductor manufacturing, all helping each other in terms of capital, in terms of application consuming, and therefore Samsung and SK Hynix became very strong leader in semiconductor, mobile phone, and consumer. The next one is Taiwan. Taiwan was very specific also. I was based in Taiwan for a few years myself. Taiwan started with the audio and toys, but also mostly from the PC motherboard for the American company manufacturing. And later on started to create their own industrial park and high-tech area in Hsinchu for becoming leaders in personal computer and peripheral, but also in semiconductor. And you have the name of the three key players, TSMC, MediaTek, and UMC from Taiwan. Very strong success. Singapore started to also do its own semiconductor manufacturing called Chartered Semiconductor on the lower part on the left side under the Temasek. Temasek is a foreign investment from Singapore government financial arm. And for 20 years, they tried to become very strong, but they didn't fully succeed and were acquired by global foundries that then set up operation in Singapore. But there is not anymore local players. But Singapore was extremely successful to attract most of the semiconductor companies worldwide, and most of them are doing front-end and even also at the beginning back-end operation in Singapore. So Micron, ST, Infineon, Global Foundry, UMC, Vanguard, and so on are now having strong manufacturing in Singapore, and the same for back-end. Indeed, in the electronic cluster of Singapore, where there is basically 70, I understood that the number now is 75,000, but 33,000 are working just in the semiconductor, and this is one of the largest manufacturing industry cluster of Singapore. Now, if we look at China later on, they arrive even later. They arrive in the year 1990s, year 2000. And of course, with the power of China, they started to become very strong in electronics itself and then in semiconductor. But China is doing a lot of subcontracting for electronic system, but China is not as strong in semiconductor itself. They do 35 to 70% of the subcontracting manufacturing of a lot of multinational company in China, but semiconductor is only 7 to 10% of their manufacturing, of the worldwide manufacturing. So if we want to summarize what was all this country, what was the ingredient of success? An electronic focus. You have seen Taiwan was a PC, Japan and Korea was consumer, Europe was telecom, of course, US and China was really on almost any kind of application. What they needed is, in fact, to have a government focus with a good education, incentive, and technology park focus. They need R&D with government funding or financial and industrial players funding. They need entrepreneur dedication, either diversification of bigger group or development of startup. And they need partnership between electronic and semiconductor and customers worldwide. So then the region can become also competitive in electronic itself. That's what, for example, India is starting to become. And the semiconductor itself will reinforce this loop of giving, let's say, the opportunity to become even stronger in both electronic and semiconductor. Now, there is a few key players. I will go very fast here, but you know there is William Shockley for the transistor and Jack Kilby for the integrated circuit. There are two Nobel Prize. There is two key people, Maurice Chang from TSMC and Pasquale Pistorio from ST Microelectronics. that created leaders in this industry. And of course, the Intel one, Andrew Grove and Gordon Moore, when Intel was really in a very strong position for 40 years. Now, let's move to the new wave of semiconductor market and application. So you have, we move from supplying industrial need. At the beginning, you have seen we are really supplying a big company doing switching system, mainframe computer, and big electronic system. Now we are answering the society call on everything. You need it for your phone, you need it for your TV, for your game, for medical, for many things, and it's really to answer the society call. Now, society call means what? Climate change, health and wellness, connectivity, Industry 4.0, and safety and connectivity. So if we deploy it for semiconductor, it is green electronics, biomedical, Internet of Things, robotics, artificial intelligence, and so on. So green electronics is almost everywhere, on energy harvesting, on solar panel, on windmill, on green appliances, on smart grid for the deployment of energy within a city and a region, and on green vehicle also. So let's look also on automotive. Automobile is a big market. You know, automotive, as I say, was having a few dollars in the car. Now it can be 1,500 for some electrical sophisticated car. So at equal volume, we can sell today 1,500 instead of selling a few dollars inside the automotive business. And therefore, this market is moving from 30 billion to 100 billion very soon. Now, on the healthcare, there is plenty of area, and healthcare is, of course, society call. There is the healthcare itself, the diagnosis, the prevention and monitoring, and the therapy. And let's look at the detail. There could be, you know, semiconductor in all bioprinting, in surgery, in surgical system, in radiology, and so on. Robotics, for example, a lot of surgery in US, 25–30% are done now with robotic. And therefore, robotics is what is just full of semiconductor inside. Next. In diagnosis, you may unfortunately remember the COVID, but you know, there is detection on some electronic board of any kind of disease, not only the COVID, but many others that can be done by putting just a little bit of your blood or saliva and detect if you are under, let's say, specific disease and so on. And this is, of course, million, if not hundred of millions of pieces. And then the one in the lifestyle and wellness. You all have, in particular the young people, all what is portable headset, the smartwatch, the wearable biosensor, and so on. And all of that, you know, is only working because inside there is chip. So, and the IoT is one of the key also volume of development. Let's look at the IoT, you know, was started from at the beginning, the limited local control of your lighting, of the smoke detector, of the heating system in your home. Now you can, from Singapore or from Costa Rica, you can remotely control all your home, whatever it is located. In Europe, in US, in Asia, you can really open the window, set up the light, look at the camera, check the alarm, check outside. You can do everything because there is IoT, Internet of Things, and this is plenty of chips, not only within your monitoring system, but also in every of your camera and control system of Internet of Things. Therefore, the Industry 4.0 is going to bring a lot of capability. And the most important are the robotics and the data center with all artificial intelligence. The robotics is almost moving everywhere. At the beginning, it was really for the manufacturing of automotive, but now we go to pharmaceutical, to household robotics, to medical, and even to very advanced robotic. This one is a picture of the one in Dubai at the Scientific Museum. And I have seen, let's say, a presentation by the robot. The robot is speaking exactly as a movement of his hand and so on when he's speaking exactly like a human body. So extremely sophisticated number of complexity of chips inside, processor, graphics, sensors, and so on. So the last one is, of course, the data center. I'm sure you are aware that all the service industry is working on data centers, and this is a typical one. This is the one that are used now in a deep level of concentration of data for communication, for storage, for the blockchain, artificial intelligence, and so on. And it looks like a data center, but if you just back. Yeah, if you open any of the drawer of this big kind of heavy machinery, you open the drawer and it's full again of processor, image processing, power semiconductor, and memories. So this data center, the main cost is just the semiconductor inside. The rest is air conditioning to make it suitable for using it in very intensive use. So let's work on now that we have defined the application which are really going in volume. Let's look at the positioning and the challenge of the top 20 players. First of all, there is not so many. The 1 year represents almost 70% of the total industry. There is 100 of players in semiconductor, but the top 20 are very significant one. But they are organized in a very unusual way. You have the one doing only the design, what we call the fabless. That means that they don't have manufacturing or even technology. They just design, what we call the fabless. And you can recognize the name of NVIDIA, Qualcomm, Broadcom, AMD, and MediaTek. Then you have the one on the right side, which is opposite. They don't do any design. They just do manufacturing of the design on the wafers, the front end. And here you have the top three, TSMC from Taiwan, GlobalFoundries, which is from US, but coming from the sovereign fund of Abu Dhabi, and UMC, Taiwanese also. And then you have the one in the middle doing everything. They do the design, the front end, the back end, the customer support and application and so on. And here you have, again, the American one, the Korean one, the European one, and one Japanese. So it shows that the way of operating is different than the usual industry. The top 20, they are also very limited in terms of countries. You have Samsung and Hynix from Korea, Infineon, ST, and NXP in Europe. And Europe is only basically 4 or 5 countries: Germany, France, Italy, Netherlands, and Ireland. Then you have Taiwan, and you have Japan, and you have America. So basically, there is 10 to 12 countries having significant manufacturing capabilities in front end. This is unusual. If you look at car manufacturing, there is 50 countries in the world doing car manufacturing, whatever their local brand or the international one. So this is the latest result of 2023. We don't have yet 2024, but I will show you later on. You can see that, there is 3 groups. The top 3 or 4, which have almost a revenue of $60 billion. Then the one of memory and the one of design house, which are in the range of 25 billion, and all the other IDM in the range of 10 to 12 billion. Now, during the year 2003 versus 2022, some of them were not starting to decrease, some of them were continuing to increase. But you can see that the next one, in 2024, it is the opposite. The ones that has been decreasing are now increasing significantly, and the ones that was still increasing last year are now decreasing. Why? Because they are serving different marketplace. Let's have the next one. In fact, the one that I was showing before, Intel, AMD, Broadcom, Qualcomm, NVIDIA, and so on, they are serving a very few number of applications, 5 or 6, and with a few number of product. So memories, micro, modem, chipset, and so on, for cellular phone, PC, TV, and game, and so on. But then there is a list of other players, ST, TI, Renesas, analog device, microchip. And these ones are serving the automotive, the industrial, the computer peripheral, the consumer, the IoT, medical drone, and many others. There is 100 of other applications. What are the differences? The barrier of entry are different. The first category is requiring ultra high level of speed and integration of the process. So they are the one that either by design or technology makes the difference. The other part is requiring less speed and ability to integrate, but you need a combination of digital and analog and power, because the transistor can be used also for analog and power capability. And you need a strong level of relationship with people, in particular in the automotive and industrial. So these two markets are developing in parallel each other. Of course, the one on the top try to do a little bit of the market of the one below, and also the one below try to do a little bit of the application of the one above. But generally, they are also quite well in synchronism together. Now, you have seen that the manufacturing is a challenge. Indeed, for the most sophisticated manufacturing, going down to 2 nanometers distance between the two transistors, you need wafer fab, which are costing almost 20 billion. And if you look at the past, a factory in 1955 was 20 million. In fact, it was 2 million at the time. It's 20 million of today, US dollars. So in 65 years, the cost of manufacturing from the most sophisticated technology has been moving from 20 million to 20 billion. Not all fab are 20 billion. There is plenty of fab between 5 and 10 billion today, most of them. The 20 billion, if the one of the most sophisticated part, let's say technology, and there is only a few countries having that capabilities, mostly Korea and Taiwan. So to develop this manufacturing, they need, some of them have the ability to do it themselves because they are very profitable, like TSMC in particular. But Samsung, Intel is less and less capable today, but because they are suffering on their investment and technology development to catch up with the competition. So, but if you look at the country of the world, they are trying to help all the other players to develop. You have USA, we have a CHIP Act, industry contract for 53 billion. Europe also, China is even bigger, and India is even starting to put 10 billion to allocate. So you can see that the cost of entry of manufacturing is quite heavy. Now, I am talking here mostly about front-end. The back-end operation is much less expensive. Back-end operation can be between 500 million and 1 billion, and not 5 or 10 or 20 billion. Now, let's look at, in fact, the landscape and the geography. On front-end, you have basically 8 countries. You have even 7 countries. You have USA, well, you have EU, which is 5 countries. You have China, Japan, Korea, Taiwan, and Singapore. So you have 2 kind of blocks. The one having a huge population, USA, EU, China, and then you have the one having a smaller population, Japan, Korea, Taiwan, Singapore. Singapore, as you know, is 5.9 million people, but they have, of course, a very strong GDP, and they have huge manufacturing infrastructure for semiconductor. There is tens of fab in Singapore between front-end and back-end. In back-end, it's even more limited in terms of countries. Only China, Malaysia, and Philippines. There is a few others, but they are quite not as significant, which are really the one where back-end operations are done. So what is, let's say, the future that we can foresee? ASEAN economy is a reference. Malaysia is moving now from back-end operation for manufacturing to front-end, because they are starting to have almost a 50 years experience in manufacturing. Then you have the Philippines, which is trying to increase also drastically their capacity. And you have a new potential hub in the coming years, which could be Vietnam. So ASEAN is a place also, but there is also next one. You have India. India is starting to move in the right direction. Remember that India was really software, but finally, in the last few years, India recognized that if you want to be independent and autonomous, you need, let's say, to have also the hardware. So a lot of companies are investing manufacturing for electronics, Samsung, Huawei, Foxconn, Xiaomi, and they have a plan to set up semiconductor capacity, one front-end, 2 back-end, and so on, in partnership with local multinational company. So the landscape, I'm sure there will be long-term evolution, and Latin America could be the next step after ASEAN, and later on Africa and so on. Why not? You need to have big region of the world having a certain level of autonomy. Now, semiconductor, as I said, is at the core of almost everything now in the economy. It's like the steel, you know, that was in the 1900s. If you have steel in the 1900s, you were able to do everything. Car, ships, train, aircraft, and so on and so on. You were a very powerful country in 1900 if you were really having the ability to manufacture steel in large volume and with high level of quality. The same for now semiconductor. It is, of course, at the core of the electronics industry itself, but also at the process manufacturing and also the service providers. All the e-commerce, internet, social media companies, telecom are relying on data center and telecommunication, and therefore on semiconductor. So semiconductor is not becoming fashionable just because the newspaper has been talking about it in the last 3 years, but because it is really becoming strategic. Now, indeed, if you look at the future, whatever research program, development and innovation program, infrastructure program, in energy, in robotics, in artificial intelligence, in building, in aerospace, in IoT, on everything, in e-service, in utility, and so on, everything is relying more and more in large volume on semiconductor capability. So you can see that indeed Wall Street realized that very quickly. In year 2015, the market cap of all the players in semiconductor listed on the Nasdaq and New York Stock Exchange was having $1 trillion. And suddenly, in less than 7 years, this has been multiplied by 5.4. In 2022, I don't have the number of 2023, but in 2022, which was at the time of very high growth of the semiconductor industry, the market cap listed in New York was 4.5 trillion. So multiply in 7 years by 4.5 the market cap in the financial world. You can see that this was the recognition of the strategic importance of the semiconductor industry. And in fact, the latest challenge, it is almost close to my conclusion, is in fact the human resources. I did this chart because when I am doing this conference to business school and university, they are not so much knowledgeable on semiconductor and electronics in general, even if they are well educated. And I try to tell them, that they can do a very fantastic career in this industry. Why? Because there is a strong demand of not only engineers and technicians, but also people in marketing, in accounting, in communication, in finance, in everything, in engineering, in quality, in sustainability, and so on, for the semiconductor industry. And therefore, the challenge for all the industry worldwide is to find the human resources. So, and the next one is showing you that indeed there is a huge number of positions that any student can, let's say, achieve for his career. Here you can see the number of positions on the right side in design, manufacturing, engineering, quality, strategic planning, communication, sales, finance, and so on. You have all the level of the hierarchy, from the operator to the CEO, and there is plenty of, I put here the minimum to be inside the chart. And then the key countries which are opportunity also to have their career all over the world. Singapore, Taiwan, USA, Europe, Korea, Japan, China, and later on many others. So the key takeaway to conclude my presentation is semiconductor is really at the core of almost all other industry and services, and its pervasiveness. That means its ability to really go inside every application in large volume looks unlimited. The second point is, of course, there is ups and downs in this industry. It's a very cyclical industry because it's always difficult to have the manufacturing having the right capacity for the demand, because it's very capital intensive and very complex to set up. But with its incredibly high level of innovation, the semiconductor industry will continue to provide huge opportunity of employment in the long run. This despite ups and downs in the market trend. And the non-high-tech company should start to look for knowledge and resources related to this business. Because, people in insurance, people in banks, people in construction, they feel that, they are far from this complex industry. But, people doing building today are using semiconductor to control almost everything inside, from the elevator to the consumption to the IoT for the lighting, for the security, for everything. The insurance company, if they have to insure semiconductor fab, which are costing 5 to 10 billion and even tomorrow 20 billion, the risk assessment requires the knowledge of this industry. The banks for M&A, for analysts and investment, have also to understand very well this industry. So this industry may look sometimes coming from another planet, but it is from Earth, and it is an industry that will spread to all the different sectors of the economy worldwide. Thank you very much, and I hope that this is giving you a good understanding of this industry.
Thank you so much, Mr. Guibert. We have a question here from Don Ignacio Trejos. Don Ignacio?
related with the company.
In your presentation, a reference to ARM, the research and design company, which is located in the UK.
Yeah.
ARM.
You are from ARM?
No,
Yes.
asking.
Ah, okay.
Mhm.
Yeah, well, ARM is very well known, so.
What is your question? I'm sorry.
Just that I didn't see that in the presentation, and their designs are the basis of many things like Qualcomm's.
Sure, they are at the core of most, including all the IDM also, and not only the design house and so on. I'm trying to remain on the semiconductor design of the circuit, not, let's say, the one at the core of it, the one setting up the standard for processor, FPU, and so on and so on. I'm trying to remain strictly on the top 20 players in the semiconductor manufacturing design front-end, back-end. Sorry for, but it is obviously
Thank you very much.
Very well known. Any other question?
Don Sergio Panayagua.
Yes, thank you very much for the wonderful. Thank you very much for the wonderful presentation. I have a question regarding Moore's law, which we know is coming to an end because at some point the gate will be one atom thick, and then we can go smaller than that. So,
Yeah.
what are your predictions on what's going to happen once we reach that point?
I don't have this prediction myself. There is a specialist of R&D on the kind of material and lithography that they will be able to use to go down. I understood that right now in R&D they are working down to 2 and even 1.4 nanometers. But you may have a limit. But you know, when I started, the limit was in micron. I remember when I was in TI, going down below 1 micron was a kind of black hole. And today we are going to be close to 1 nanometer, and it's still done on silicon and with a kind of extension of the Moore law, even if it's not exactly the one that was set up by Gordon Moore before. So I cannot answer this question because it required strong knowledge of different material. The gallium arsenide, there is many other possibility, but it could be even neuronal, it could be from many other high-tech developments that goes beyond my knowledge and my ability, let's say, to set up.
Thank you.
Well, thank you so much, Mr. Guibert, for this detailed and interesting lecture of the development of the semiconductor industry and how the assembly process of the semiconductors work. That it's a very complex process, and it's amazing what you said, that creating a finished chip and its evolution has 50 billion transistors. Wow. I really appreciate today your lecture, Mr. Guibert. I don't know if there's any more who has a query, a question. I see
Murillo.
Murillo. Thank you.
Hello?
Adelante, JD Murillo.
Open the microphone.
You have your microphone on mute.
En mute, yes, Murillo. Tenés your contact. Check what is the message.
His microphone doesn't work.
Okay.
If you want, you can put the query on the chat and we will tell Mr. Guibert.
Yeah.
Oh, he's doing it right now.
Mm-hmm.
Okay, he puts on the chat that he wants to ask Professor on the CHIPS Act, as Costa Rica is part of it.
To my knowledge, not. There is very strict limitation of benefiting from the CHIP Act from US. Companies are required to, let's say, really do manufacturing most of the time with a condition of on intellectual property, on access to technologies, and so on. So they have already given significant, let's say, investment to some American company, but also to some foreign companies. There is Global Foundries and TSMC that have benefited of this, but there is also the local one, Texas Instruments, Micron, and Intel, and so on.
Thank you so much, Mr. Guibert. Ambassador Rojas, I don't know if you have anything else for a closure.
Really not. I was impressed with the quantity of people was connected. I think it was 348. Oh my, you're famous, my friend. No, thank you very much, Francois, because it's Friday, it's night, and you are here with us, sharing your knowledge with us. Thank you very much.
A great pleasure. I hope that this is giving you the global view, and I will be ready to, if a larger scope of industrial and institution and so on would like to have the conference in Costa Rica. I will be very glad to participate.
Thank you so much, Mr. Guibert. Thank you, Ambassador Rojas, David Lee, and our colleagues from the Diplomacia Económica, Marilis Villegas, and Marlene Brenes, that I see them connected. So thank you very much, Mr. Guibert. If you can share with us your presentation, we will greatly appreciate it.
This is my 40 years experience, and I am keeping it for me because this is my intellectual property.
Perfect. Comprehensive. Thank you very much, Mr. Guibert, and thank you all for connecting to this interesting lecture. Have a very nice day and night in Asia. Thank you.
Thank you very much for your time. A pleasure, an honor and a pleasure for me.
Thank you.